smart contract rabbit hole. So we realized that in the Ethereum ecosystem and in overall in every smart contracting platform, because of its um, deterministic nature, you cannot consume information from outside the blockchain, and it's a very similar problem to what our customers were telling us, which is how can I know what's the state of something in the internet without having to trust a single point of failure or a single entity reporting the information. How to retrieve data without having to trust the messenger. So we realized that, and that's exactly what we are trying to solve. They call this the Oracle problem. How do you put information into smart contracts without becoming yourself a central point of failure that can introduce like arbitrarity into the contract? Because if you Ethereum is awesome because it gives you a decentralized store for your code, a decentralized need some way to feed information, to feed data into those contracts trustlessly for many use cases, which rely on having information from the real world or from something that needs to happen in order to release some funds or to transfer some property or for any other flashy use case that we want to envision for smart contracts.
So, what are some of the use cases specifically where a trusted party would be a real problem? Because, like, I right now I can only see the ability to do this with a trusted party. So, I'm I'm curious the use cases for that, and then I'm excited to really go into how you guys solve the problem.
Yeah. When we talk about smart contracts, we want to think that we are talking about disintermediation, about not having to rely on trusted third parties, which is a system that works quite flawlessly for many use cases, and it has been working for centuries. And the, probably there's no need to replace all of that, but there are many other use use cases that in which something so simple or so elegant as a smart contract platform joined with a trustless data provider, which is the idea of an oracle, is capable of solving in a way that can enable new use cases, that can enable a number of um, mm, new possibilities for new businesses, for peer-to-peer uh, betting, insurance, all kind of things that we have been doing through intermediaries, through marketplaces, through all of these companies that are very legitimate, but now we have a way to opt out.
So, like, for insurance is a great example. There's a lot of regulation and there's a lot of extra bullshit on top of this third party system to keep that third party honest. And with this, you could kind of get rid of all those checks and balances because it's already internally automated with checks and balances. Okay, that's pretty cool. Um, so yeah, how do we bridge Meatspace to? I mean, it doesn't make any sense. Like, I don't understand how you can have a. Is this live stream going? It is nice. I just don't understand how we can bridge Meatspace to the blockchain like without a trusted third party. Uh, Open my eyes.
So the way that you can jump in any point. So the the we're working. The concept is we would be pulling from open APIs, and so open data sources. And the way that the decentralized Oracle network that Witnet's building will have headless browsers that are able to collect data and yeah, headless browser. Do you want to explain
Yeah,
that?
yeah, yeah. Headless browsers are automated, um, like um, automated browsers that don't have an interface but are controlled programmatically. So we what we are creating is this network of nodes which have this headless browser that you can script. You can send a request to the network and say, I want 10 of these nodes to go to this particular URL, retrieve the data, parse it as JSON or whatever it is, and take this particular portion of information, like maybe you are requesting the temperature in Berlin, so you need to make a request to one or two or many weather APIs with this pointing to the weather in Berlin, and then taking the particular data, then you can transform it maybe from Fahrenheit to Celsius or what or whatever you need in your use case, and then you aggregate then the request you send to the network is made in such a way that it's completely explicit about how data aggregates across different sources, and then how it's aggregated from the results that different nodes are reporting, because it could differ over time, for example, or some of the nodes may be tampered with and they could try to manipulate the final results. So you can actually filter the outliers. You can use a very simple consensus functions that remove the outliers, that remove, for example, those who are reporting a value which is more than X away from the average, or from twice the average, like the standard deviation, or things like that. So what you get is that you can make with Witnet, you will be able to create smart contracts from Ethereum that are explicit about how data will be retrieved, aggregated, and reported back to the smart contracts in explicit way, so that you perfectly know how that data will be handled and what you will get in the future, because you can schedule this data retrieval for the future for many use cases, like that depend on the outcome of a future event or something, many things like that.
So these headless browsers, these nodes, how are they connected to each other, and like what is the incentive mechanism that makes them want to report?
Yeah, actually, we run our own network, which is separate from Ethereum, which is important for the incentives to work as expected and not to be influenced by other exogenous factors like gas price or other things that are natural to the Ethereum ecosystem. Um, so this platform is, let's say, chain agnostic, but has this integration with Ethereum through bridge nodes, which act as interfaces that also allow the Ethereum smart contract developers to post requests to the webnet network without having to handle the WIT token, like the token that is native to the webnet network. And this token is fundamental for the incentives of the network, for keeping every node honest in the short and in the long term. And the way it works is that if you are running a webnet node, you are resolving this data request. You are doing this work of not actively but automatically retrieving data from URLs and transforming in whatever way and sending it back to the smart contracts in exchange for a portion, a share of the fees that the requesters are attaching to their requests. And then there's also for the sake of guaranteeing that these incentives are um, preserved and that everyone abides by the protocol, there's a reputation system that it's like a separate token inside the network that it's not transferable, but it gets automatically transferred from the ones who make their work properly, who report the same value as the consensus, and is detracted from those who try to deceive, to those who try to tamper with the data requests. And all this reputation, there's a fixed amount of reputation points, and it's affected by a progressive demurrage function, which means that only because you have reputation, you're losing reputation, and the more reputation you have, the more quickly you lose it. And this is very interesting because it allows us to algorithmically fix fix a ceiling to the reputation points that someone can have, and so that we can limit the impact that some exit scammer could have on the system, because we can make impossible for anyone to hold reputation more quickly than they lose it just because they are a big player. We can put that ceiling in 50%, so that there's no possibility for a 51 the ceiling, like the maximum. We can put it on 50% to prevent 51% attacks, or we can put it in 1% or as low as that, in order to ensure decentralization. So this is a system in which there's a convergence to equal players. If you leave the system, run it for infinite time, everyone finish will finish having the same reputation, and everyone will have like the same weight and the same power in the network.
So is there a block reward in Witnet? Or is there like some kind of reward that's currency that's generated to incentivize the network?
Yeah, actually, yes. We have an emission mechanism for the token, which is similar to the Bitcoin one, for example. So it has like a halving over time, and this is important for rewarding early adopters of the protocol, rewarding early witnesses, which is how we call these nodes that are retrieving the data, that are like the equivalent of the miners. And also it's important for the ecosystem to have um, a Slack for doing price discovery for the data requests, because you are incentivizing through the block rewards. You are subsidizing the data requests, so it gives the ecosystem time for discovering what's the sensible price, what's the value of that the network is providing to the ecosystem.
And then I think this is probably a common question, but what happens, and you kind of talked about it with the ceilings, but if you have, a group of 30 nodes or something like that that are trying to gain reputation, but they're like, there's one target that they're looking for to like obscure. It's like, yeah, we want to just if someone asks who's president of the United States right now, we're gonna say, Barry Silbert. He's gonna be president anytime someone says that. But everything else we're gonna do right. And so you got this big network of nodes that are gaining reputation as much as they can, and then they're like, no, this one thing is false. How do you stop that?
I guess that could be quite problematic for oracle networks in which the oracles are actual people who can design that kind of collusion. Or but for automated oracles, there's a big barrier for the the one the nodes misbehaving, or the hackers, the black hat hackers behind those, to modify the source of the software, to have the intelligence to tell those requests apart from the rest, and only to lie in these particular cases, which is it's a very but that's not the radical solution, of course. The thing is that under the assumption of the network having a big number of witness nodes, you have very, very little uh, certainty that some data request will be assigned to a particular cluster of nodes that you own, or nodes that you control, or nodes that are cooperating with you, because these requests are assigned randomly to those nodes. So it's if you are requesting maybe 20, you have a replication factor of 20, which means that you are like hiding 20 witness nodes to retrieve that information, and then the network is formed by 10,000 nodes. You would need to attack, or to take control of the entire network, to make sure that you have a high probability of tampering with the result of that data request.
Very cool. So that makes a lot more sense. You're sectoring off to just like a small percentage of the network. And like, how do you guys scale to get to that point where you are large? Like, what's your roadmap like for specifically getting these numbers of nodes and like pushing it? Where are you now?
Yeah, so right now we have a testnet launch in end of January, or Q1, and so end of January is our goal. And besides, we're working with open source, specifically Rust developers for the development of the protocol and getting contributions. In terms of the gaining critical mass of the community of witnesses, that's going to be through a lot of just general. Oh, well, there's incentives through mining, early mining, like you'll receive a higher rate, compared to over time. But generally speaking, we want to make sure that we have access to the kind of the kind of community that believes that like mission critical smart contracts are necessary, and that they understand the relation of data to how mission critical these smart contracts are. And so, we have the Ethereum bridge. Obviously, Ethereum is the most active community, the largest community. We're also going to have an Archain node as well, and the Archain bridge, excuse me. So, and then there's no reason that we can't have any other blockchain bridge as well. And so, all of these sort of the 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 method of how smart contracts are going to retrieve data, how they get data, and the fidelity of the data is going to be something that we're pushing, and we're just going to be asking a lot of questions in terms of people's values, like what are you building, why are you building it, why is the data important to you, we want to bang that drum beat and make sure that everyone can answer that. And if somebody wants to choose a centralized data source, that's fine. I mean, everyone has their own sovereign ability to build what they want to build and for the reasons they want to build it. But we believe that it's important to ask these questions of why we're building this and why we're providing it and why people want it.
Have you guys ever heard of DAppNode? It sounds like a really cool application to get on there because people aren't gonna. It's like here's a node you can just like turn on, and they're not gonna mess with it because they're just hoping to get a little bit of money for running their server, right? So that sounds cool. And I'm also curious, like the blockchain itself, is it a fork of Ethereum or is it its own completely built from scratch? Like, how did you guys? It has its own native token and a reputation token. Are there other things you can do with it, or is it really slimmed down just for that?
Yeah, it has been built from scratch because we have a lot of many particular requirements that would be very difficult to deal with if we forked Ethereum, for example. So this Witness Rust, which is the name of the like the full node software, it's written in Rust because it's Rust is awesome because it gives us top performance with memory safety and with guarantees of doing concurrency without having to fear some of the classical problems of concurrent programming, and also it makes the app uh, very efficient so that we have very low barriers to entry so that anyone can run a node in a Raspberry Pi, for example, which is very important for adoption. But then um, the question, the last question was about,
The blockchain
yeah,
itself,
the blockchain itself.
smart contracts in the future, as well as that decision. Yeah, because it sounds like you have a bridge, right? So that's how you start that.
Yeah, as I said, it has a lot of particularities like the reputation system and so on that would be difficult to build on top of a proof of work chain or things like that. So we prefer to start anew, but we don't really want to reinvent the wheel. So it's a really bare bone blockchain that that every feature it has is like pluggable, so you can decouple those and you can use this very simple chain that we have created to extend it in many ways. We expect other decentralized whatever networks to leverage the work that we are doing now.
That's cool. So do you guys work with the parody crew often on the whole Rust gang? You know.
Not yet, but we'd like to. Well, I also want to say, so just to clarify, so we released a prototype, like a technology preview of the GUI for the network in September, on September 6th, and we have like high level features that will be available. That so there's attestation request, which is like the data request. So you're saying I want data from X source. I want X numbers of iterations of it, multiplied by whatever. And then there's there's going to be a basic smart contract feature, which will have some automation features. It's not as robust as say Solidity, but so there are. Th- as Adon said, we're not really reinventing the wheel for smart contract platforms. It's more like a very specialized network for the data, the data oracle, requests. So
And then for oracles in general, like there's it sounds like you guys have a very specific like this is a browser that's asking information from the internet from different sources. I mean, is there a way to? I guess that's the hack where, like, if I want a sensor in a fish tank, I would have to just put that on the internet, and this kind of thing. Like, do you have any other solutions for, like, if you want something that's not necessarily on the internet? Like, is that out of scope right now, or I don't know. I'm just curious. Like, how do you guys do these unique requests?
Well, that's interesting. Like this IoT use case for sensors, but the thing is that even if you even if you have a decentralized Oracle network, which is like the messenger for the data, the broker for the data into your smart contract, there are a lot of consideration about the sources. So a sensor is a single source, is a single source of truth, and it doesn't really matter. It's very nice to make sure that your contract is consuming the data that the source is producing, but then you are still relying on a single source, which should be okay for many cases. But the thing is that if you want to connect a sensor to this kind of data shovel that moves data from the source to your contract, um, this kind of crowded attestation or retrieval is not that that useful. Yeah, but the way is probably that, like to create an API for your sensors, like to create an interface that is easy to interact with, and yeah, that's something that any developer is familiar with. So we can expect people to do it like that. If we wanted to not to rely on web technologies for that because they were not supposed to, and if we are consuming uh, data from devices that naturally speak other protocols like MQTT or any other IoT protocols, uh, the, you arguably, yeah, anyone could create a MQTT bridge for the WNET network so that you can consume that without having to rely on the internet infrastructure.
Well, that's really interesting. I mean, that would be a separate client, I assume, right? And so then you'd have multiple clients on the network that would be trying to reach consensus on a blockchain. Oh, that's scary. That's pretty scary. Uh, but uh, but that's pretty cool, man. What about hey, do you guys have any questions? Yeah, yeah.
Um, yeah, I was trying to get the name of the group again. So, where is it that you guys work? WebNet. Okay. Oh, Witnet. Sorry about that. Yep. And yeah, because I've worked in the IoT space as well, and very interested in how the real world can be represented on the blockchain in a kind of as true as possible kind of way. And do you do many things around having redundant sensors and fusing that data at maybe a smart contract level, or having some data analytics where you might have multiple sensors in the same thing, and then you look for common noise patterns, and you say, well, look, chances are they're not spoofing that because it's not a constant, and it has this similar noise profile. Have you looked at considerations like that?
Yeah, that's a very cool use case, and that's actually something that you should be able to do with the testnet that we are releasing next quarter, because with the with the Radon language, which is like the programming language for the data request, you can specify multiple sources, which are your multiple sensors. Then you get to transform the data, like to normalize it. Maybe if you need it as a float, not an integer or whatever things you want to operate on them. And then there's an aggregation phase in which you get to declare a function that will filter out outliers, for example, like like exactly as you say, to remove noise, and then calculate the average, or remove those who are twice away from the average than the standard deviation or things like that. Any kind of statistical map reduce that you want to perform on the data that the sensors are giving out, and then have it reported to your smart contract. So that's a perfect fit.
And I guess further to that, checking that is it just mathematical functions like standard deviation and simple things, or is it somewhat codified? Like, can I say if it doesn't have this noise profile, like more so if I'm using the noise as a indication or a fingerprint of a sensor in that body of water, I know that if it's got if it moves in a similar way, and those four sensors, yeah. So one thing would be to get rid of outliers, but the other one might be to look for something that doesn't look like it is a sensor. Is it purely functions, or is it like?
We have thought of that, but it's actually out of the scope of the first testnet. But yeah, that's something that we want to work later on.
I'm going to show another question.
Yeah, so you have a Q1 launch coming up, which is pretty cool. Do you see anything slowing? Like, how do you actually bring this from testnet to? Because this is a testnet launch. What's the roadmap for testnet to real? I mean, what does it look like? Obviously, it's a whole guessing game. We'll see how it all works, but just in general.
Well, we plan to have like many functionality levels covered by subsequent test nets. So actually for the first test net, there will be the capability of posting data requests into the network, running your own node, or have the nodes in the network to retrieve, aggregate, and deliver that data, and also to have like these silly smart contracts, like these conditional payments, in which you get money to go to Alice or Bob, depending on whether tomorrow will be sunny in Berlin, for example. But then, from then on, we will be heavily working on these bridge nodes, which connect WebNet to Ethereum and to other smart contracting platforms, and we expect most of the use to come in through those bridges, which are fundamental for the success or adoption of the protocol. But we're really excited, because if we do good, Ethereum will do good, and we really want it to happen. And if Ethereum does good, we will do it also. So it's like a perfect symbiotic.
Very cool. Hey, thank you guys so much for pulling this off. We're going to move on to the next one, but thank you. So yeah, next is Jordi Baylina, who's going to teach us all how to do zk-snarks. But we're going to need to rearrange the chairs just a little bit, because it's going to be crowded, so we're going to maximize. So if you guys can all just stand up, and we can really like push this table back a little bit, make some more space there, and push these chairs back a little bit, get another row of chairs. Yeah, let's just keep that. If you guys can move some bags behind you, and oh, I see. Yeah, rows like this. Yeah, I think we'll need some more chairs.
What's the whiteboard? What's working?
Oh yeah. And there's some whiteboard markers.
Hello, hello. Okay, guys, let's start. I think we are all more or less ready. Well, first of all, thank you all to coming this early morning for listening this stuff. I think it's a cool stuff, but it's a little. Well, I think it's not that hard. And the idea is to demystify a little bit zk-snarks and see how we can create these circuits and how we can really create zero knowledge. And we see that this technology starts to being available. Okay, so well, I'm Jordi Baylina. I'm from Iron3 project. In this case, we're working on an identity project that we're using mainly zk-snarks. All the development that you will see today, we have done in this context, in the Iron3 project. So if you have any questions, we are right here about that. But let's start. So the idea of today is just create a real example of a circuit, of a zero knowledge. Just try to create the circuit, create the proof, then verify the proof, and verify the proof on chain, and just check everything that works, everything together. So let's start. First, I want to do a small introduction of what's zero knowledge. I expect that most of you already know. If you are here, probably it's because you are interested on. But I just want to explain you what's zero knowledge from a more practical side. Okay, so the kind of zero knowledge that we are working is quite generic, but there is we have what we call it a circuit. Sometimes we call it circuit or we call it program. Okay, but at the end is a program that in general have an input data. Okay, and if you want an output data. The input data, sometimes we can divide it in private input and public input. Okay? Sir? Black is. Okay, so we have a circuit. Let's see, that's a deterministic circuit. So it's a circuit that you put an input here, and at the output we have automatically a value. For example, if the circuit is just an addition, you just put here, for example, a 3 and here a 2, and at the output I have a 5. Okay, that would be a typical circuit on that. We see that the inputs can be private or public. What we really are proving when we are creating a zero knowledge proof, what we are proving is that we know a private input that when we execute with this public input, it gives this output. So mainly in a circuit, we just generate a proof. You generate a proof, and to verify the proof, we need to pass the proof itself. Let's call it P, the proof. And we need to pass also, well, of course, the circuit, what we are proving. We are proving against this circuit. Let's put it here, the circuit. Okay? And then we need to pass also the private input, sorry, the public input. The public input and the output. Okay? So the verification, we just pass this function, and this can return true or false. We can only generate this proof if we really know the input. And not only the input, but all the intermediate values here. In this case, in the case of an addition, this is quite easy, okay? Because if I have a 5, everybody knows two numbers that when we add them together are 5, okay? But imagine that here is a hash function, okay? And I have only one private input, which is the value that I want to hash, okay? So in this case, what I want to prove is that I know an input, I know some value, that when I hash it, it gives this specific output. So if I pass here in the verification, you pass the output that you want. In this case, so the public input is nothing. We don't have public input in this circuit. Okay, we have the proof, and of course the circuit is just the hash function. Okay, so in this case we can prove that we know this input at the hash. Okay. let me just put, for example, some example circuits so that we can see that the usage of that. Okay? For example, typical thing is it's the eraser. This is not very good. Okay? Imagine that I have a circuit that verifies a Merkle tree, just a generic Merkle tree. Okay? So imagine that I have a Merkle tree. Where the leads, for example, are public keys of people, that represents people. Okay? So I want to prove, for example, one thing that I want to prove is that given, so here is, I now, for example, as an input I have, for example, a Merkle proof, okay? Maybe I have my public key, my private key, okay? And the output is the root of the Merkle tree. So I just generate a circuit that I give a private key. With this private key, internally I'll calculate the public key. So I do a multiplication, I get a public key. Okay? And then I just have different hashes. Okay? So this I hash, see if I hash them together. So I just hash all them together. And at the output I just generate. So with this public key, I generate the keys. If these inputs are private, so what I'm doing here, I am proving that I have a private key that whose public key is inside this Merkle tree. But I'm not revealing, because this is a private input, I'm not revealing, of course, what's my private key, nor what's my public key. So I'm one member here. I'm saying that I'm one member here. That's really, it's valid, it's inside here, it's a valid one, but I'm not saying who is that. That's, for example, very important, for example, for a voting system. A voting system, when you want to vote, you need to be sure that you are in a census. You are in the list of the people that can vote. Okay? So if here is the list of the people that can vote, you just get the list, which is public. You get the Merkle proof. You have, of course, your private key. You generate a proof that, of course, you now your private key and this Merkle proof of the place, and then you calculate the root. And anybody can be sure that you have this private key. If you don't have that private key, you should not be able to see that proof. Okay? So these are kind of typical examples of things that can be done. Sometimes are normal operations that don't need to be even private or public, but you are, for example, just to save a space. This is very important, for example, for scaling. I can generate, for example, many transactions, okay, that I can generate transactions off chain, and then I can prove that I executed those transactions in the right way, and then I just put this proof in a normal in an on-chain. Okay.
So can you explain the merge in the context of when you're using that?
Sorry.
Can you explain it in that context of when you're
Well, this is a voting system. It's an example, but for example, in a system where you have a lot of transactions, when you want to scale transactions, mainly is that. So the idea is that you have. This is it's just an example. Probably it's not the best example. I know that I hear it's probably not the best example for that. I think that Amir just showed you a much better example, much more simple, and probably much more useful at this stage. But there are many. Zero knowledge proof are this circuit can be anything, and this can, for example, be but this could be this means just you put some input and maybe you can prove with this circuit that you are, for example, paying the right taxes. But the nice thing of that is that because you don't reveal the input, you are not saying how much money you have and where it comes from and whatever. You are just proving that you are doing the things in the right way, so that you are following, so you are doing a specific calculus. Okay, so there are many applications. There was a good talk right now with the talk about different applications, and it's huge, and it's through the computation. There is a lot of applications on that. Okay, so what we are focusing in this session, we are mainly going to construct a circuit. Okay, so the first circuit that we want to construct is a very simple circuit. The circuit that we will generate is a circuit that we are able to factor a big number. Okay, so that means that given a number, for example, if I give you 33, okay, so please let me know what two numbers, when you multiply them together, it gives 33. In this case, it's quite easy because it's a small number, and everybody already thinks that 11 and 3 gives 33, so it's quite easy. But if I give you a huge number, 256 bits long number, this is quite more difficult. Okay, so mainly the circuit that we are going to build is quite simple. So the circuit is going to be, let's do a circuit. The input is going to be, let's say, A and B. These are going to be private inputs. Let's put here private. And the output is going to be public, okay? And this is going to be just the multiplication. That means that if this is C, that means that C equals A times B. Okay? So this circuit is going to be only valid if I have two numbers. Now, two numbers that when you multiply them together are C. But of course, without telling you which numbers are A and B. I'm proving that I know those numbers, but I don't want to tell you those numbers. Okay? So we are going to build a circuit. Here, the circuit, there is a trick. We are going to solve at the end of the session, but just because I'm sure that somebody is asking us, is already asking. There is a trivial solution to this problem. Okay? So if one of those numbers is 1 and the other is just C, then you can find it quite easy. Okay? So in some way, we need also to prove that none of these numbers is 1. We just, if somebody comes to this mind, just forget about that. Okay? 1 cannot be. We will explain later in the session how can we do that. Okay? So let's focus first in doing the trivial circuit, which is just as normal and simple multiplication. Okay? So let's start. Let's start. I don't know if you are ready with the laptop. Okay, first of all, I know that some of you is gonna do the stuff. If there is somebody has any problem, here's maybe some people can help on each other. Okay, the first is the prerequisites. Of course, you need to install Node. Just one side note about Node.js. Okay, is the last stable version is, I think, is 8 dot something. And if you use the last unstable version, which is 10 dot something, it's going to be much faster. And this is quite important in this stuff, mainly because the last version of Node.js it supports native big numbers, big integers, and then the operations are quite faster. So if you install that 10 dot something node, is much better. It also works with 8, but it will go a little bit more slower. Well, it's something like 10 times more slower. So it's an important gain that we get in the number 10. Okay. Last version, just as a side note, for example, Chrome supports the big number in JavaScript. This is like an extension. It's not in the last standard. Okay. But Firefox, for example, doesn't support currently. I don't know if maybe last week they changed it, but it's not yet. Okay. So that's just to know. This is some improvements. Big numbers in cryptography, they are used quite a lot. So it's a good thing that JavaScript start implementing these big numbers. Okay, so the first thing that we are going to do once we have this node installed, so it's not that I expect that most of you already have it, so we need to install these two packages. Circom, which is the compiler of the circuit, so it's a special compiler for this kind of circuits, and then snark.js, which is just a working tool for creating the proofs, for verifying the proofs, and for all the stuff that's in there. So just make sure that you npm install -g. Maybe some of you have some problems when you install -g because you need some privileged sudo, but if anybody has some problems on that, just let me know for later. Okay, but everybody that knows a little bit of Node, it should be quite easy to install those packages. Okay, so once you have these two circuits, the first thing is, well, let's create a circuit. Okay, just of course, in a normal situation, you would just create a normal repository and all that stuff. But for this case, just open a directory, an empty directory, okay, and create this kind of hello world. So this is the circuit that we are doing here. Okay, and now we are going to see this circuit. Let me see if I can do it a little bigger. Yeah, it's if you see my Twitter, it's there, but the spell it's iron3.io/blog/Circom and snark.js tutorial with hyphens in the middle .html. I don't know if you see my Twitter, I just published it there like 1 hour ago. So. Jordi Baylina. Just this is my Twitter account. I just retweeted the link right there. Yep. Yeah, I will show you later maybe some more complex circuits, so you will see the powerful in there. But yeah, it's what you're saying. In general, you cannot build loops if you can build constant time loops. Okay, so if there is this circuit has like 2 stages. Okay, one first stage we just compute the constraints. Okay, and the second stage that just you just compute the witness. Okay, and all that stuff. Of course, you need to be able what are the constraints beforehand. Okay, so it cannot be variable related. Okay. Yeah, you can test it in general. Should work. Okay, but just the idea is that already tells you where it's. So you can. Yeah, at the end, the best thing is you think one good thing to think about this is like in electronics. Okay, so you have components, you have circuits, and the idea is that, for example, you have a gate, a normal electronic gate, an AND gate, or an XOR gate. Okay, so give an input and you automatically have an output. If you have a loop, then you will have. It means that you have 10 gates. Okay, we'll see some examples later. We'll see some complex code written in Circom, and you will see more the powerful on that. Okay, just here is just we are starting just doing like a hello world in here. Okay, this is very easy, but I want to run in all the cycle. This is a hello world method. I want to run in a cycle with a very simple circuit on that. Okay. So let's see this. So this is a very small circuit, but let's analyze what's this circuit about. Okay. First of all, you see here, this is a template. and then you have an instantiation of that template that's here that's called mine. Okay, so this language mainly you can define templates of components. For example, I can define a template which is an AND gate or a NOR gate or maybe another or a multiplier or a binarizing or a hash function. Okay, and then even those templates, we will see that these templates can have even parameters. So I can have, for example, another of variable number of bits or whatever. Okay, so it's like a template is like a class. Is what we understand as a class in a normal. So it does not do nothing, but you can instantiate as many components as you want, and they can be different. The people that know C++, the concept is a template too. So you can create a template of classes. Okay, this is a template of components. Okay, and in the last line, we just instantiate. We are really creating. We are instantiating that template. In this case, where this template is called multiplier, and here we are instantiating a multiplier. All the circuits in Circom it's like a little bit like C. They must have a component called main, which is the important, the principal, the main component on that. Okay, and what has this template? Because this template has 3 signals, 2 inputs that are private and 1 output. That's mainly what we are defining here. Just 2 inputs, 1 output. And we are already telling here that those inputs are private. If we don't say nothing, that means they're public. But that's how we define that. Okay? And then this program has only one thing, which is very easy. So we just connect the signal C to this A times B. Okay? You see here this special operator is not an equal because we are connecting signals. Okay? We'll see that we trade different what are signals and variables. Okay? But here is just a normal signal that we are just saying that the C is output A plus B. So here is what we're saying. Here we'll see, well, this is a circuit. You can just create it. Okay? Be sure that's more or less well written. If not, you will get some error later. Okay, and let's compile the circuit. Compiling the circuit is as easy as just running Circom, and then you just put circuit, your name of your file, circom.circom, -o, and the output is a compiled circuit. It's a JSON, but it's an internal format. So just compile it, and it should run. Okay. Did anybody compile it? Yeah, more or less okay. Yeah. Okay. Great. So we already have the circuit. Okay. So from now on, we already have used the Circom, which is the compiler, and now we are start using Snark.js, which is the tool just to start using this circuit for. Okay, so of course you can do a snark.js.help. You will see all the options there. Mainly is the best documentation that's written right now. Just doing this help. Okay, and the first thing that we can do is, for example, you can run snark.js. Well, you see, for example, info and the name of the circuit. You can avoid if you want the circuit.json. By default, it looks for a file that's called circuit.json. If it's different, you can put different. But if it's called circuit.json, you can just avoid the -c and just do snarks info. Okay, and it should give you some parameters of the circuit. In this case, should be 2 private inputs, 1 output, 1 constraint. No, very easy circuit. Okay, general circuits have millions or even billions of constraints. Okay. Yeah, sure. Yeah, that's important. That's a little bit internally how the circuits works, but at the end here we have a circuit. Okay, but when we are proving when we say that we are proving a zero knowledge proof, what we are really proving is that those signals, inputs, outputs, and maybe some internal circuits, they follow some constraints. In this case, for example, the constraint is that C must be equal to A times B. Okay? So when we are building a circuit, when we are saying that we are compiling a circuit, one of the things that we are doing is mainly looking for those constraints and creating this list of constraints. Let me give you, for example, some examples, okay? And here of some interesting constraints. One interesting thing to do is, for example, to here, for example, you see a constraint of an XOR. Okay, the constraint of XOR means that Xout, so the output, must be equal to A plus B minus 2AB. Okay, this is a constraint. So if you have an XOR, means that the inputs must follow this function. Of course, we understand as binary, but if you see that when A and B are both ones, this means that this is 1, and then it's 2 minus 2, this is 0. Okay? When one of those is 1, this term is 0, and the other, of course, is 1. Okay? And when all other zeros, this is 0. So you see that this circuit, okay, this is these constraints follow a normal XOR, follows a normal XOR circuit. Okay? Of course, this is only valid when the inputs are binary. But here in the Circom, all the signals are not only binary; they are a number between 0 and the order of the curve of zk-snarks, which is this number is close to 253, something like that. Okay, so it's a huge number. Okay, so for a normal circuit like XOR, this would be one constraint, and probably we also want to create another constraints to force these signals that are binary. So in this case, for example, we should add, for example, that to be a binary, I can say that I minus 1, this must be equals to 0. Okay? With a constraint like this, I'm forcing that this equation is going to be only valid when A is 0, because this term is going to be 0, or when A is 1. If it's something else, this constraint is not going to be valid. Okay? So if I want to create a single XOR, what I need to create is I need to create these two constraints. Okay? So when we are creating, just compiling a circuit, one of the things that we are doing is just generating all those constraints. Okay? Yeah. This is a very important concept. Let's move on. If you want to see those constraints, you can just do print constraints on your circuit. You will see that you have a single constraint. Maybe you will see that the format is a little bit strange. It's not it's not the usual way that we're used to read, because we are in zk-snarks, we are putting all the constraints in a specific format. Okay, I just print you the format because I think it's good to see it at least once. In general, the generic form of constraints for a zk-snarks, we put it in this way. Okay, so A1, which is A11 S1 plus A12 S2 plus Sn, AN Sn, all that times, I'm going to run B1 S1 plus B2 S2 plus Bn Sn minus C1 S1 plus C2 S2 plus Cn Sn this equals 0. Okay, and the same thing for A2. A221 is 1 plus A22 is 2 plus A2NSN times B1 is 1 plus, sorry, B2 is 1 plus B22 2 plus B2 and SN minus C2 n SN plus C2 no, this is C1 no C2n C2 C no, 3 1 n this is C2n C no 3 1 2 2 n no 3 no B1 a moment this is B1 2 this and 1 and 2 and then this is C and C11, C12, C1n, and this is C21, C22, and this is C2n Sn equals 0. Okay, and then just as many constraints as we want. Okay, but we put it in this format. Okay, this is we call the term A, this is the term B, and this is the term C. Okay, these are linear combinations of the signals. Okay, the signals are the one that's variable, and A1, A2 are parameters of the circuit. Each circuit has this A1, A2, B1, B2, these coefficients defined. Okay, so at the end, you see that compiling a circuit means just finding these matrices of coefficients and all that stuff. Okay, so okay, we already have the circuit. We see the circuit compiled, and now we have to do something that's very specific to the zk-snarks, and this probably is the biggest criticism that has the zk-snarks. Zk-snarks, I would say that it's a perfect technology except for this trusted setup. Okay, zk-snarks, they require, and this is quite specific to this technology, they require that for each circuit we run what we call a trusted setup. That means is that we need to get some random values, do some computations on that random values, keep the computation, so keep those values, but the initial random, the seeds, the initial random, some toxic values, we have to throw it away. And we need to be sure that we throw them away. If we don't throw them away, that means that all the system doesn't work. Okay, and this is a famous trusted setup. Here is what, for example, the Zcash people, they use these ceremonies and all this story. And this is a full topic just by itself, how to solve that. But it's a problem that once we solve, I would say that that's happened. But this is also the biggest criticism, okay? Because at the end, we end up having to trust this initial setup. There are some interesting solutions for that. It's multi-party computations and some trusted hardware, or just people just drilling computers, and there are things. It's a very mystic thing, but that's important to know. Okay, so what we are doing here is we're just running a trusted setup. It's a trusted setup because you trust yourself. Okay, so it's not a very good thing here. This should be running in a different way, but at least to start working on that, we just need to generate those parameters in our computer. Okay, so just run the trusted setup on here, and after you run the trusted setup, mainly what it does, this setup, is generate two files. Okay, one proving key and one verification key. Okay, this is the result of the trusted. This is the result of the trusted setup. Okay, we will need the proving key to generate proofs, and we will need the verification key to verify that those proofs are valid. Okay, run it. Hope that everybody you should see the files. You know, by default they are called this way. Of course, you can change the parameters and change the names and all that stuff. Okay, but you should see those keys somewhere in that place. Yeah. Yeah, there are some. Here is a research topic, and there are some works that maybe it's for some circuits like that. Some of them divide this trusted setup like in two steps. One shared, important with many people and very trusted setup, and then small setups that are not so necessary for security. And there are setups that you can just like add like entropy of that people can do the entropy just by adding new information. You know, there are different topics. It's a topic research. It's something that it may change in the future, but right now I would say yes. So for each circuit needs its own setup. So for each circuit you will have a verification key and a proving key, and you need to be sure that the toxic values are thrown away. Okay. So we already have run this ceremony of drilling computers and being sure that we don't know these toxic values, okay? And we have this result, the proving key and the verification key, okay? So now, next step is to generate the proof, okay? But before generating the proof, okay, what mainly we need to do is like execute the circuit, okay? We need to know all these signals, and in this case in the case of this is very trivial because we have only two inputs and one output. So mainly what we need to do is mainly compute the output. Okay, that's the only thing. But when we have an important circuit that we have very intermediate signals, imagine a hash function. You need to do a lot of steps in this steps. You mean like, for example, if you have here maybe you have a door, okay. And then you have like another door, okay, and then you have here maybe another door, maybe let's put here an XOR, okay. So here in a circuit like that, you see that of course you put an input, but you need to calculate all these intermediate signals that are in the circuit, okay. So these signals, or sometimes they call it wires, okay, because wires of a circuit, okay. This also, the full set is what we call it the witness. Okay, this witness is all this information that we do. When you execute the circuit, when we do the circuit, it's like we plug the circuit and we just have some values. Okay, and this is important so we need to do that every time that we want to generate a proof. Okay, mainly, if we see from the constraints, is we are just computing all these signals, all these variables that we are sure that matches all the constraints. Okay, but we need all the signals, inputs, outputs, and intermediary signals. We have the full set. We know how the circuit is at all. Okay, this is what we call the witness. Okay, so the first step is compute this witness. Okay, so to calculate this witness, first of all, we need to, we need an input, okay? This depends on the circuit. So first of all, we need to tell what's this going to be this input, this witness. So we just need the inputs of the circuit. So let's create a file which is called input.json, okay? And put the input signals, in this case, something like that. Of course, you can put the values you want there. This is just an example. No. In this case, for example, I have a NAND. So here maybe imagine I have four inputs, okay? So imagine that here I put a 0, a 0, a 1, and a 0. Okay, this is the input of the computing the witness means this is 0 and 0 is 0, NAND, means that this is a 1. Okay? No, in this case, you are not throwing away nothing. You are just executing you are executing the circuit. You are executing the program. Okay. So that means that you are putting an input into the circuit, and you are computing all the intermediate steps, and of course the output. Okay. So you are just executing this, but you need to keep all the intermediate states, because at the end, what we are proving is that these intermediate states, that are the signals, they match all the constraints that we defined before. Okay? No, the ceremony we already did the ceremony. We already burned this is done. Okay, but then the ceremony, we know that this is only not needed for one circuit. Okay, you don't care what input and what output. You have just the board. You know, it's like this is, and of course, once we have the circuit, we can generate as many proof with different values as we want. But we need to do it. This trusted ceremony, we need to do it when we design a new circuit. Once the signature is designed and the people start using and generating proof with different inputs and different outputs, you don't need to do the trusted setup again, of course. No. You cannot use the same proof for different circuits, and yeah, sometimes there is some tricks. That's, for example, the trusted ceremony of zk-snarks is already done. Sometimes what I do is I may use this circuit to run it in a specific way, maybe it's putting some inputs to 0 or just using some parts of the circuit in some way, so that I don't need to run this trusted ceremony. But I'm running the same circuit. The only thing is I'm running the same circuit with specific values, and there are some tricks on that. But the circuit is the circuit. You do the trusted ceremony for that circuit, and that's attached to that circuit. The verification key and the proving key are attached to that circuit. Okay. Yeah, this is what we call it embedded. This is very interesting, but it's hard. Yeah, it's hard. Yeah, there are some research on that. Yeah, this is what we call interactive, and this is very interesting. It's interactive. I know rentrancy. So just verifying a zk-snark inside a zk-snark. Yeah, this is very interesting, and this is we can talk about later. Okay, that's one of the things that you can do, but it's hard. You know, the problem is that verifying a circuit is it's a lot of constraints. So. Okay. Okay, so once we have the input, we just calculate the witness. Okay, you will see that the output is going to be a file called witness.json, and you will see there all the signals. In this case, we have very few signals. You will have 4 signals. In this case, you have A, B, C, and you have a very special signal that's called the unity. That's in the beginning. That's always 1, and that's like a special signal. It's like, in electronics, it would be like the power on, you know, the plus 5 volts. You see, for the people that does electronics, that means that. Okay, you need that special signal. Okay, but you will see it in all the circuits, and in general, it's the first, at least in this implementation, we put it at the beginning. But okay. Okay, once we have the circuit, okay, we already run the circuit, and now we have to actually generate the proof. Okay. So we have the input, we have the trusted setup. So right now, to generate the proof, we just take the proving key, the witness, and with the proving key of the circuit and the witness of the circuit, we generate the proof of the circuit. So if you run that, you will see that this generates two files. One, of course, is the proof itself, okay, and the other is just a subset of the witness that mainly is the public part of the witness. That is only the public input and the public input and the output, nothing else. We just remove all the intermediary signals and of course the private signals. This is the part that you want to pass in general to the verifier. So when you want to verify something, means that you are able to, so you run the circuit where all those